Okay, let's get going. So this will be a video introduction to the workshop uh, concerning Maxwell's equations. So we're going to look at partial derivatives and functions of several variables, and we will do that in the context of Maxwell's equations. So Maxwell's equations are given as we see here. Let me just change to black. And well, we see that we are concerned with two vector functions or vector fields, the electric field E and the magnetic flux density B. And these are functions of four variables. We have three spatial variables, so we will consider the position vectors R depending on three variables x, y, and z. And typically we will write them like this. So we have x times I, where I is the first standard vector, y times j, where j is the second standard vector, and z times k, where k is the third standard vector. And actually for this workshop we will, instead of x, y, and z, use x1, x2, x3. So yeah, just to be sure on what we're talking about. So if we have three coordinate axes, x, y, and z axis, then I, j, and k are the unit vectors. They're also given as these, and a vector x in space is then given by the three coordinates x1, x2, x3. So if we want to look at it as a column vector, it's just the same as writing as so. Oh, 3. And then our two functions E and B, they are vector fields, which means that you plug in some coordinates. So we have the spatial coordinate and the time, and then what you get out is a vector. So for example, if we consider E, so the vector you get E of x and t, well, you can also compose that into a first coordinate, which is of course then multiplied by I, a second coordinate which is multiplied by j, and a third coordinate multiplied by k. So that is the setup. And let us just move to the first exercise. So in the first exercise, we consider a static electric field. So we have no time dependence here. It's only x. So E is only depending on x. And we have some notation. X with two bars, that is the length of the vector x. So it is basically Pythagorean theorem that gives this length, that it is x1 squared plus x2 squared plus x3 squared, and then the square root of that. And we have to show, well, it's basically the electric field generated by an electric charge situated at the origin, and we have to show that in fact E is equal to the gradient minus the gradient of a function v called the potential, where v is given like this. Okay, so let's see. Up here we had some things. So in this box down here, there's some stuff that if you don't know, it's nice to know. So we can write this length of x or norm of x as x1 squared plus x2 squared plus x3 squared, and then to the power 1/2. And that's because taking the square root, as we see down here, if we have the square root here, so b is 2 and a is 1, well, then it's just the same as raising to the power 1/2. And that is sometimes useful. So if we use that, we can write our vector function E as q divided by 4 pi epsilon 0, and then 1 over, then we had the length here, so this is basically just the norm of x to the power 3. So note that we have 3 halves here, which means that we should take the square root and then we should raise it to the power 3. or do it the other way around, raise to the power 3 and then take the square root. And then what we have here is just the vector x written with ij and k. So we can identify by considering e1, well, that just corresponds to taking the first component here, so that is basically just this x1 we get down here. And you can do the same for x2 and so on. Okay. And then we have the potential, V. And that was given by Q divided by 4 pi epsilon 0, and then 1 over the length of x. And again, I've written the length of x using this guy up here, where we use the square root. And in fact, 1 over a square root, we can use this rule here to say that's basically just the same as saying whatever we had in the denominator raised to the negative power instead. And when the nice thing about this formula is when we have to differentiate, we have a very neat formula for differentiating stuff like this. We just take our power down in front and then subtract one from the power. So that's the whole deal about rewriting it this way. It makes it easier when we differentiate. Because when we want to find the gradient, well, what we want to do is the gradient is given as we take the first partial derivative of v as the first coordinate, the second partial derivative as the second coordinate, and third partial derivative as the third coordinate. So that's basically it. So when we differentiate, let's try and do the first one. So we say dv dx1. That is, well, if you recall it, we have it down here. Q divided by 4 pi epsilon 0, and then x1 squared plus x2 squared plus x3 squared to the power minus 1/2. And then we should differentiate that. So the constant doesn't matter, but we have to differentiate here with respect to x1. So the function we're differentiating now is a composite function, where we have something like this over here, s to some power, but instead of writing s, we plug in x1 squared plus x2 squared plus x3 squared. So we have a composite function, and when we differentiate stuff like that, we have to use the chain rule in this box. So we have to differentiate first what is f in this formula. That is basically s to minus 1/2, and then plug in g, that's the x1 squared plus x2 squared plus x3 squared, and then multiply with the derivative of g. And this is for one variable, but when we do the partial derivative with respect to x1, well, basically we have to take this guy inside here, differentiate partially with respect to x1, and multiply on what we got from the outer function. So if we do it, let's see, q divided by 4 pi epsilon 0, and then we use this neat formula we had down here, this one, to say, okay, minus 1/2 goes in front, and then we keep the inner function, that's from the chain rule, and then we had to subtract 1 from this minus 1/2, which gives minus 3/2. Okay, but we're not done. This is the first bit here, but we're still missing this, so we have to do the partial derivative of the inner function. Oh, like that. And if we do it, well, only x1 here depends on, or the first term depends on x1, so the rest are just 0. So in the end, we get, well, we get a 2 down in front. We use the same formula as before, 2 down in front, but we also have this 1/2, so they actually cancel, and we're just left with x1. So we will get minus q over 4 pi epsilon 0, and then we get x1 squared plus x2 squared plus x3 squared to the minus 3 halves, and then multiply it with x1. And if we use this first rule over here to rewrite the parentheses, we can actually write it as minus q divided by 4 pi epsilon 0, and then we have x1 divided by x1 squared plus x2 squared plus x3 squared, all to the power 3 halves. So we just take care of this minus in the power by saying it's instead 1 over and whatever we had here. Okay, and if we look at it, if we compare this guy to this guy, we see that only a minus is the difference. We have a minus here, so at least for the first component, we have then shown that this formula holds. And you can do exactly the same calculations with x2 and x3